Radioactivity is basically when you have a nucleus and it's not stable. So because it's not stable, it spontaneously begins to emit little tiny particles trying to achieve stability. And it can do this in several ways, as I'll show you here in a second. So you have a nucleus. It's not stable. So what makes up the nucleus? What particles do we find in the nucleus? Remember? Protons and neutrons. So something about the ratio, the number of the protons to neutrons we'll see, makes it not stable. Because it doesn't have a good ratio, it's going to try to spit out pieces and undergo changes until it tries to get a nice stable ratio of protons to neutrons. And that ratio is different, we'll see, for every element. Actually, we won't see too much of it, but we'll briefly mention it. Come back in 111, I'll teach you all kinds of fun stuff. So, as a little reminder, how do we write isotopic symbols? Well, we write them like this, right? So you put the symbol, we put down here, we put what's called the atomic number. The atomic number is the number of what? You remember? Protons. That's the number above the symbol on the periodic table. And then we write up here, the top left, the mass number. Remember what the mass number is? Protons and neutrons, because those are the particles that have all the mass. So pretty much all the mass comes from the nucleus, the protons and the neutrons. Again, this is a review. So, but now we're going to add symbols for 3 new particles. Well, not new particles, just new symbols. So a proton, you could write a proton with a symbol that looks like this. One proton and neutron. So that's a new symbol. Neutron, I could write a symbol like this. An electron, I could begin to write a symbol like this. So 0 protons and neutrons. We're going to put actually -1 proton in this, because it is this, like a proton in terms of charge, but just a flip sign. So that's our symbols we're going to use in this nuclear chapter here for proton, neutron, and electron. Again, this is way back from chapter like 3 or something, way back. I don't know what it was, way back. Yeah.
A bit confused. So for proton symbol, what is the top one?
What's the top one mean? What's the top one mean?
Mass number.
Which means what? You just tell me, man.
But then, like, the atomic.
What's the mass number mean?
The protons and the
Protons and the neutrons. So if it's got 1 proton and no neutrons, it's still 1 here.
Right.
Here it has 1 neutron but no protons, so it's still 1 here. That's protons and neutrons. Protons and neutrons. Okay, so let's talk about. Come on. There we go. So, like I said, why is there radiation? Because the nucleus is either too large or it doesn't have a good ratio of neutrons to protons. So again, it's all about the nucleus. We do not care about the electrons when it comes to radiation and nuclear chemistry. We care about the nucleus, the protons and the neutrons. So what's that ratio? Again, I can tell you much more about this if you come back in another class, but in general, if it's a small nuclei, one of the first 20 elements or so, like hydrogen, helium, lithium, those, they need about a 1-to-1 ratio between protons and neutrons. So they have 5 protons, they want 5 neutrons. But as they get heavier, they want an increasing number of neutrons. So maybe after a while, it's 1 proton to 1 1/4 neutron. And eventually all the way up to about 1 1/2. So the really heavy ones up there, like lead, uranium, etc. If you've got 100 protons, now they want 150 neutrons, let's say. So it's 1 1/2 times. Well, if it doesn't have that ratio, then it's going to have radioactivity. It's going to try to do things to try to either spit out the extra neutrons or try to spit out the extra protons or try to turn protons into neutrons or vice versa, trying to get whatever the ideal ratio is. And again, that ratio kind of varies depending on what the element is. Okay, so we're going to look at 4/5 kinds of radiation. We're going to look at alpha, beta, gamma, and positrons. I want to cover each of these, so you'll see them on the next slide. So here's a little chart that shows what is the ideal ratio between protons and neutrons. So this is my number of neutrons over here. This is my number of protons. So this line shows when it's 1 to 1. So 20 to 20, 40 to 40. That's when it's 1 to 1. So you see, when it's down here, all the yellow ones here, these are stable. So yeah, at the lighter weight ones, it is about 1 to 1. But you see, as it gets heavier, it kind of veers more and more away from that line. Can you see how that's happening? So as they get heavier and heavier, for every proton, they actually begin to need, 1 1/4. So now it's not 40 to 40, now it's 40, now they need 50. Now it's not 80 to 80, now it's 80 to 120. So it's not 1 to 1 anymore, they need more neutrons. Again, the reason that is, so beyond this class, but basically there's this thing called the nuclear strong force. It's the glue that holds the nucleus together. And every particle in the nucleus adds some glue, whether it's a neutron or a proton. But if you add in protons, well, now you have all these positive charges, and positive charges like to do what to each other? Repel. So yeah, so you don't want to add in this more positive and positive because it makes the nucleus more unstable. So you add in more neutrons because those are neutral and they don't increase repulsion, but they do add more of this nuclear glue called the nuclear strong force. So yeah, as we get more and more positives, well, it takes more and more glue to hold it together, so we're going to put it more and more neutrons. So yes, it just kind of veers off. So there was a man named Ernest Rutherford I mentioned before. Remember way back when with the gold foil experiment, he discovered the nucleus and all this stuff. Well, he also discovered 3 types of radioactivity: alpha, beta, and gamma. And these are the Greek letters for that. These are the lowercase alpha, beta, and gamma. So what he did was he had a bit of a radioactive substance and it was spitting out radiation, and then he took that radiation and he passed it between 2 charged plates. So one plate had a negative charge, one plate had a positive charge. And when it went through, then he put over here on the side just a piece of some photographic film. And he noticed he was getting dots or like light forming on the film at 3 different spots. So some of the radiation was going straight on through and not being at all affected by the positive negative. Some was going down away from the positive towards the negative. Some was going up away from the negative towards the positive. So let's see. What can I reason out about this? So the radiation that was going down like this. What do you know about that radiation? What could you figure out about that radiation? It must be positively charged. Why? Because it's being attracted to the negative, and it's being then repelled by the positive. So the one going down, alpha rays, must be positively charged. That's one thing. How about the betas then, that are going up towards the positive and away from the negatives?
Negatively charged.
They must be negatively charged. And the gammas that just go straight through, they must be neutral. You are so smart. Look at you. Look at you. You can win a Nobel Prize too. So now what else though? What else was noticed about this? Well, the alphas, when they went through and they felt they affected that field, they moved a little bit. The betas, when they went through, got hit with that field, they moved actually then quite a bit more. So what would that kind of indicate? So this one here, then you smack it with this force and it moves a little. This one here, you smack it with the force and it moves a lot.
More negatively charged than the alpha is positively charged.
That's a possibility. It's actually not what happens, but yes, you're right. No, you're absolutely right. If it's a higher charge, you think it would have a greater effect. That is one possibility. What else might be the case about the particles? So if I flick one thing, and it barely budges, and if it's something else and it flies across the room, what's probably true about the two?
The mass?
The mass. Yeah, the one that barely moves when I flick it, what?
It has law mass. Wait, are you flicking barely moves?
Yeah, barely moves. It must be heavier, right? Right? The one I flick and it goes flying must have lighter weight. Exactly right. So this one is a heavier positive particle. This is a lighter weight negative. This one is just neutral. So so you are exactly right. Congratulations on your Nobel Prize. Alpha particles are identical to a helium nuclei. So helium, is number 2 on the periodic table, right? So it has 2 protons, also has 2 neutrons. and it has, but again, no electrons, so it means it's 2 positive. So yes, that is a big particle. It's basically just, son of a gun. It's a helium nuclei. It's a big boy. 2 protons, 2 neutrons. Has a mass of about 4 AMUs then. Electrons, they are just electrons. Beta particles, they are just electrons. So electrons, we know, have basically no mass compared to protons and neutrons. So yes, much lighter weight than alpha particles. And just has a negative charge. So yes, super lightweight, which is why it went flying, and negative charge, which is why it went towards the positive and away from the negative. So that's our betas. And then the last ones are the gammas. The gammas are not actually particles at all. They are just pure photons, which you could argue is a particle, but they really have no mass, and they're neutral. So you're right. So neutral. The gamma is neutral. So heavy positive particle, super lightweight negative particle, just neutral energy. That's the gamma. Yeah.
Is that why the protons are in the center? Because they weigh so much, so like they're not the ones that are revolving, or is that a whole different reason?
I don't know if that's why.
It's like since they're so heavy, like it take more energy to revolve, or I don't know. I'm just.
I mean, just trying to figure out how do you answer why. I mean, on the physics stuff, I'm trying to think. Yeah, as other stuff. I mean, it makes sense what you're saying, but I don't know. I mean, it might be possible to orbit them. I guess I don't know. Yeah. I don't know. Now the other one is called a positron, which sounds goofy because it literally is a positive electron, which makes no sense because we know electrons are negative. But positrons, they have the exact same mass as an electron, exact same charge, but just is flipped. It's positive, not negative, so we call it a positron, the positive electron. So that's the 4th type we'll see. Same mass as an electron or a beta particle, but it's positive 1 instead of negative 1. Okay. Okay, got that? Okay, so let's spend a little time on each of these, and I'll just kind of discuss each of the radiations. So let's look at alpha. So again, alpha, I already said, you got that down. It's when your nucleus is so unstable. So back up. So a nucleus is unstable when it doesn't have the right ratio of protons to neutrons, right? That's what makes it unstable. Well, some of the ones that are like really heavy, we'll see like all of the ones, for example, like that are way up to like past uranium on your table. So your thorium, plutonium, all these big heavy ones, they are just so unstable. It won't actually help them out to just turn 1 proton into a neutron. They're just like, we're just way too big in general. We're going to spit out 2 of both. So they just spit out a big chunk of themselves, trying to get down to that ratio they want to be at. So alpha particle, so that's when you spit out just a big old chunk. Okay, already said all that. That should be a review. So let me show you how I can show that chemically. I literally already said that on the previous slide. There was nothing on that slide that was new. So we're going to write what's called a nuclear equation. So I'm going to show you one. And we're going to, basically the equation, we're going to track the nucleus. We're going to track the protons and the neutrons. So let's look at uranium-238. Already uranium-238. Uranium, of course. 238 is a radioactive version of that. So uranium-238, I can write a symbol like this. So 92 means it has 92 protons, right? 238 means it has 238 protons and neutrons. So the one we start with, that's called the parent nuclide. And again, that's not stable. So what's it going to do? It's going to begin to break down and spit out pieces of itself somehow. Alphas, betas, gammas, positrons, whatever. And it's going to make what are called daughters, daughter nuclei. So the parent has daughters. I don't know why there's not sons, but there's only daughters. So they're making, biology?
Yeah, because, when the DNA and they split, they make daughter
Oh,
cells or whatever.
there you go. Why not sons? Why not?
That's why it's like it comes from biology. I don't know why.
So what do you notice, though, about these numbers between the parents and the daughters? Notice anything about them?
Atom
Oh, that would be the exact same. So 92 protons here, 90 and 2. Still 92 protons here. 238 mass number here, 234 and 4, still a total of 238 there. That's always true. So once you undergo some kind of radiation, you're still going to have the exact same number of particles before and after. You're just going to kind of shuffle them around. So yes, very important. So 92 here, 90 and 2, 92 here. 238 here, 234 plus 4, 238 here. Yes, good job. So that's it's always true in any kind of a nuclear equation. Okay, I told you all that, and I showed you all that. Okay, so now that we know that, let's just try one. Let's just try one. Let's say we're going to do, what's TH? That's my little symbol. See Avengers recently? Thorium. That's my mighty hammer. Oh yeah, that's thorium. That's thorium. So thorium 232 undergoes alpha decay. So if thorium spits out an alpha, what else must it spit out? So if that's number 90 and that's number 2, that must be what? Number what? 88, right? Something plus 2 equals 88. So what's number 88? Find it on your table. Number 88 is... What's number 88? Radium. Radium. Okay. And what's the mass number, though, of the radium? 232. And that's 4. So what's that have to be? 228. I know I told you right here, but yeah, 228. So yes, you're right. So it must be radium 228. Yes, it's not Ra, the sun god. It's not the Thor Norse god turns into Ra, the Egyptian sun god. Thorium goes to radium. But yeah, right? See how that works? 88 and 2 is 90. 228 and 4 is 232. So that makes it pretty easy to figure out. Okay, so that's an example of alpha. So again, that's what something is just big and really unstable. So what's it going to do? It's going to spit off big chunks of itself, just trying to get down to a reasonable ratio. It's not going to screw around with trying to just spit out, small little things. It's going to be, man, we are way over here. Okay, so let's try a couple here. Let's try uranium 233. I'm going to do that one with you. So, what's the atomic number of uranium? 92, right? You find it there on your periodic table. Okay, it undergoes an alpha decay, it says. So an alpha particle looks like this. Now you notice, by the way, for the alpha particles, we are not including the charge. It is technically 2 positive because we don't care about the electrons. All we care about in nuclear chemistry is protons and neutrons. So it is technically 2 positive, but you'll never see it written that way because, again, nuclear chemistry, all we care about is the nucleus. We don't care about those stupid electrons now. Okay, so let's figure out what else would it have to leave behind. So what would the atomic number be for whatever the other daughter nuclide is? That'd be 90, right? And 90 is thorium. And what mass number would it have? 233 minus 4, right? So it must be thorium 229. How'd you do? Okay, try the next one. Radium 222. So if radium 222 undergoes an alpha decay, what other daughter nuclide will it predict? Will it produce? Predict that. Okay, talk it over. What'd you get? What else? What else does radium-222 make? Are you asking somebody?
Excuse me?
Is he asking somebody what it makes?
No.
What'd you get? What else does radium-222 make? Alpha and what?
218 RN.
What's RN? Anybody know?
Right now?
Radon 218. Radon. Radon. Right on, radon. Yes, radium 222. Radium's number what? 80 something. 88, okay. So if that undergoes alpha, so it loses 2 and 4, then it must leave 218 and 86, which is, yes, radon. Okay. And what's AM? Remember what AM is? Yep, basically. Americium. It's named for America, yeah. Right. Okay, Americium-241, which you probably all have in your house, by the way.
What?
Do you know where you find that Americium-241 in your house? It's in your smoke detectors. It's in most smoke detectors. We'll explain why later if we have time. But okay. Okay. Write the equation. What else are you going to make? An alpha and, so talk it over. What's the number for americium? What's the atomic number?
86. Oh, wait. 95. Sorry.
95, okay. 95. Okay, so I must make something 237. What's 93?
Yeah.
What's NP? Another god, yeah. Exactly, Neptunium. Named for Neptune. Awesome, yeah, Neptunium-237. Sorry for my messy 37 there, but that's it. Okay, that's not bad. Pardon me?
Apologize to Neptune.
Yeah. So, okay. So, I have a little segue here, and then we'll go back into beta. Okay, so why is radiation damaging? You know, I mean, what's so bad about radiation? Well, radiation is damaging to molecules and atoms because it does what's called ionizes them. So basically what happens is it's going to smack into other molecules and ions in your body, for example, and it's going to turn them into, instead of nice, neutral, stable ions molecules, it's going to turn them into ions. So imagine, for example, then you have a nice cell here. Well, I don't know. I'm not a cell, but let's say you have an atom, and it has a nucleus, and it has all these electrons, right? And your body has trillions upon trillions of cells, right? And then you have a big old fat alpha particle comes just tearing through here. Kabam! Well, when it comes ripping through here, it might do several things. It might come through and it might knock off one of the electrons, or it might smash into the nucleus and knock off a proton or neutron. Well, when it tears off in a negative, now it leaves behind a positive charge. If it tears off a positive proton, now it leaves behind a negative charge. So now you have these nice, happy, stable neutral compounds, and you just turned them into ions. And ions, we've seen over and over, they want to find something else to make them stable, right? So if that happens, and now you have these little cells, then they have little cells made up of positive and negative ions, where they're going to grab onto the next nearest cell or atom and try to steal some of their electrons, or some of their protons, whatever they can do, trying to make them neutral. And this causes all of this kind of this chain reaction of damage. You know, so they get damaged, so they kind of reach out, and they damage the one next to them, and et cetera, et cetera. So that's called ionizing radiation. Okay, so the ability of a type of radiation to actually cause this kind of ionizing radiation is called its ionizing power. So there's two things we're concerned with radiation. One is, how well does it do this? How dangerous is it? So when it smacks into your cells, Is it going to leave a whole trail of ions in its wake, or just a few little ions? May not be as bad. So that's the ionizing power. Well, the other thing on the flip side of that is what's called the penetrating power. And that's the radiation's ability to actually penetrate, let's say, through clothing or through a wall and actually reach you, because it can't actually ionize your cells if it can't reach you in the first place. So there's ionizing power and there's penetrating power. Excuse me.
Is that when you went to the dentist, they put that little thing over you?
Mm-hmm. Okay, so let's look at alpha radiation again. Okay, so what's alpha radiation's ionizing power? Is it pretty dangerous or not? How about its penetrating power? Well, alpha radiation, we're going to see, is like the semi-truck of radioactivity. It is the big boy, because again, it's the heaviest, right? It has a mass of 4. So if an alpha particle smacks into your cell, you're going to feel it. So it has a very high ionizing power. It is the most damaging out of all the types of radiation. Okay? Okay, so it has the highest ionizing power. That's the big takeaway point. Alpha, highest ionizing power. Because again, it's the biggest, right? So if you smack one of those into you, it will definitely come to your cell and do some damage. It'll tear off some atoms or tear off some electrons and just leave a big trail of destruction, right, in its wake. But the good news is, because it's so big, it has a hard time actually penetrating through like clothing or through walls. It just can't like navigate through all the molecules in the wall and reach you. It's so big. It tends to see something else on the way and stop. So it has very low penetrating power. So that's the other good thing. But it has the lowest penetrating power. So the bad news is, if it can reach you, you're going to know it. It's going to do a lot of damage. But the good news is, it has a real hard time reaching you. I mean, you can block it. You can block alpha particles with a piece of paper. Your shirt will block alpha particles. Even actually enough air in between you and the alpha source can block it. Just because, again, it's so big, it's going to smack into something else on the way to get into you, right? So some other molecules in your clothing it'll hit, or some other molecules in the paper, or like I said, or even air molecules in the air. It'll smack those first, and it won't ever actually reach you. Okay? Like I said, so you stop a piece of paper, you can be, yeah, I'm saved, here's a piece of paper. All right, it'll totally block the alpha radiation, right, or your shirt or whatever. So that means then, if you have a low level alpha emitter outside your body, it's really not that dangerous. Okay? So you have an alpha emitter, it's low level, just spit them out every once in a while. It's clear across the room, and you're wearing your clothes, it's like naked running around or something. You're probably okay. Okay. But the flip side means, if you happen to accidentally ingest or inhale an alpha emitter, like a radioactive gas that spit out alpha particles, or you get it in your body, that is not very good at that point, because now it's inside you, and now there's nothing else to kind of block it, and it just rips through you, and it just tears apart your molecules and your cells, and does lots and lots of damage. So yes, you do not want to ingest or inhale an alpha emitter. That would be bad for your health. Which brings up a lovely, heartwarming story. Not really. I'm going to tell you about this. A few years ago in the news, there was a story about a guy named Alexander Litvinenko. He was an ex-KGB agent, and he had defected, actually, over to England, over to the UK. And apparently then the Russians were not very happy about this when he defected. So one day then he woke up back in 2006, and he was just really sick. He thought, man, I feel awful. What is going on? So he went into a hospital, and they tested, and they couldn't figure out. I was like, I don't know what's going on. And they finally figured out he had been poisoned with an alpha emitter called polonium-210. So apparently, like I said, some Russian or whoever came by to pick up some polonium on his Wheaties, and he ate it, didn't know it or whatever, and it was just tearing him apart from the inside, and he was dead in about 3 weeks. So yes, horrible way to go if you accidentally get alpha emitters inside your body. Bad thing, right? So you want to keep those outside if you possibly can, right? Yes, keep alpha emitters outside. So, how about beta? Now, beta, as I said, those are little lightweight particles. They are the same as an electron. But what really happens when a nucleus spits out a beta particle is this big thing right here that I want to highlight. Is it going to do it for me? No, it's not. This right here. What really happens is a neutron gets turned into a proton. And I'll show you that here on the next slide. But that's the big takeaway. When you spit out a beta particle, really what you're doing is that ratio of protons to neutrons is just totally out of whack. So you're trying to get it stabilized. So what do? Well, you take one of those neutrons and you turn it into a proton because you were short on protons. So try the beta and see if that fixes it. So again, there's lots of different things we can do. So let me show you on the next slide an actual reaction, and then we'll kind of prove that a neutron must become a proton. Excuse me. Okay, so let's look here. Here's my beta particle. No, you know that. Okay, here we go. Radium-228 is a beta emitter. Okay? So, radium-228, I would write an equation just like this, and again, same as the other ones. The left side atomic numbers and the right side atomic numbers always add up to be the same. The left and right mass numbers add up to be the same. So help me out on radium-228. How many protons does radium-228 have? How many? I'm sorry, I couldn't hear you. Did you say something? Not a trick question. That would be the easiest one. How many protons? 88. Thank you. If it has 88 protons, how many neutrons must it have had?
140.
228 minus 88, right? So 140 neutrons, right? Then it becomes actinium-228. How many protons does actinium-228 have? 89. How many neutrons must it have then? 228 minus 89. So yes, between the left and the right side, it gained a proton and lost a neutron. So yes, we took a neutron and we turned it into a proton. We turned a neutron into a proton. Now, right now though, our charges wouldn't be balanced. I have 88 positives on the left, 89 positives on the right. So in order to make that the same, I have a negative electron. So that negative 89 makes both sides 88 and 88 positives. So that's why there's a negative charge given off. But that's basically it. Because it adds up, right? 88, 89 and negative 1 is 88. 228, 228 and 0 is 228. Still works the exact same way. So, but remember that a neutron is turned into a proton. Okay, let's try one. Potassium-40 is another beta emitter. It's potassium-40. What's the atomic number for potassium? What is it? 19, yes, 19. And it undergoes beta, so I'm going to put my little beta symbol, an electron. So what must the atomic number be of my other daughter nuclide? What and minus 1 gives me 19.
18.
Nope, 18 and minus 1 gives me 17.
20.
Because something minus 1 has to give me 19. So it has to be 20. 20. And 20 is what element? Okay. So what's the mass number for the calcium have to be? Still 40. 0 and something is 40, so it must be 40. There you go. So calcium-40. Okay, try the next one. Helium-6. If helium-6 undergoes beta emission or beta decay, what else would it leave behind? A beta particle and what other daughter nuclide? Okay, what'd you get? What else? Lithium what? Lithium 6, right? Absolutely, lithium 6. So helium 6 is number 2. So if it spits out a beta, well, 3 minus 1 is 2, but this still stays 6. So lithium 6. And did you do the next one? Sodium 24? What else did you get? Magnesium 24, right? Okay. Questions? Pretty easy, right? Pretty straightforward. Just got to add them up. Okay. Well, if the alpha is the big giant semi-truck, the beta, like I said, is much smaller, right? Its mass is a fraction of an alpha. Therefore, that means it's not nearly as damaging when it smacks into you. So it has a much lower ionizing power compared to the alpha. It's kind of like the middle of the road ionizing power. It's not the most, it's not the least, kind of the middle of the road. But since it is smaller, it means it can actually more easily than sneak through your clothes or sneak through a wall or things like that and reach you. So it actually has then greater penetrating power. So now you actually need a thick piece of wood or a really dense piece of metal, something like that can actually stop it from actually reaching you. So not as damaging, not as ionizing, but it can actually penetrate easily then through the air, through your clothing, and reach you now at this point. So to that end then, actually a low-level beta emitter is actually more dangerous outside your body than a low-level alpha, because again, the alpha wouldn't probably even reach you, because like I said, your clothes would stop it, the air would stop it. But a beta actually would just go right through your clothes and actually, cause some damage. But on the flip side, if you accidentally ate some, or you were poisoned by the Russians because they hate you or something, it wouldn't be nearly as bad as eating the alpha, because it would actually penetrate then actually out of your body pretty quickly, and it would just be it would just actually leave your body quickly, whereas the alpha would actually come aside and it would stop and keep doing damage, because it wouldn't actually penetrate through your body. Yeah.
How would you get? How would your body rid of radiation if you accidentally ate it?
Well, it depends. It depends on a few factors. It depends, I guess, first off, on the actual kind of the nuclide it is. Is it hydrogen? Is it lithium? Is it sodium? What is it? That kind of depends on part of it, and it also depends then on something called the half-life, because we'll see in a little bit that they're not all created equal. Some of these beta emitters are spitting out a beta particle once every 1,000 years, and some are doing it 5 million times a second. Well, so the ones that are doing it very quickly, they are actually gone in a heartbeat. And gone in a heartbeat. So you do eat it. Let's say, but it kind of spits them all out, and it's done, and it's gone, and it's all used up. So it kind of depends on the kind and on how active it is. We'll see, or how hot the radioactive sample is. But there's no one common answer I can give you for all of them. Like I said, it really depends. Was it lithium, sodium, potassium? What was it that was supposed to be beta particle? Yeah.
For the guy who ingested the alpha parts, how long did it take them to figure out what he was putting in there?
I don't know, actually. I'm not sure exactly how long it was.
They're written on it.
They're like, oh, I don't know.
Yeah. I don't have any idea. Yeah, I remember reading about it. in the news years ago. And then gamma, I said, is not really a particle at all, right? Gamma is just, it's just pure photon of light or of energy in a sense. So it's just pure light. Again, it has no mass, has no protons, has no neutrons. So its symbol is often just written like this, a gamma and 0, 0, because it has no protons or neutrons. So normally, a gamma emission actually happens then in conjunction with something else. So you spit out then an alpha particle and just some gamma energy. Or you spit out a beta and some gamma energy. So it's not like you're going to have just the gamma by itself. It's going to come with something else. Again, it's very high energy. In keeping with our little superhero thing, this is the stuff that we all know turns you into the Hulk, right? Gamma rays, that's what turned Bruce Banner into the Hulk. So this is gamma rays. So no charge, no mass, etc. But it's normally made with something else. So for example, earlier I showed you this reaction. Uranium-238 underwent an alpha decay, became thorium-234. Well, and plus a buttload of energy. The buttload of energy is the gammas. But you can't really balance that, right? You can't say, oh, was it 1 or was it 47? Because it's 0, 0. So you can't really balance it. But it's kind of saying, yes. So gamma happens with something else. Gamma happens with a beta or with an alpha or with a positron or things like that, we'll see. Okay, well, gammas then, they have no real mass, right? So if they smack into you then, they're not going to be nearly as damaging. So they're going to have the lowest ionizing power. Because again, they're super, super tiny. I mean, they basically have no mass. But they're so super tiny, they can just sneak right through your clothes, just sneak right through the wall, and just reach you really easily. So they have the highest penetrating power. Okay? Oops. Oh, what the heck happened there? So lowest ionizing, but they have the highest penetrating power. So now to block that, you got to have several inches of highly dense lead or big slabs of concrete if you want to block the gamma. Okay? Okay. So we went from the heaviest was the most damaging but the least penetrating, and now the lightest is the least damaging but the most penetrating. That should kind of make sense, hopefully. Okay, now the other one I mentioned was this weird one called the positron, which is like a positive electron. It is just the flip side of the beta. So, in the beta, you're spitting out a little negative charge. Now we're going to spit out a little positive charge. In the beta, a neutron turns into a proton. In the positron, a proton turns into a neutron. Proton turns into a neutron. So that's the big deal. So now that ratio is not quite right, so it's gonna try to lose some of that positive charge, cause some repulsion, try to turn it into some neutron, make some more glue. So it's gonna try to, again, just trying different things. Nuclei just try different things. So let's write a reaction for that now. So now our symbol, instead of 0, -1, is gonna be 0 + 1. But it all works the same, it all adds up. Right, so like here, phosphorus 30. Oh, and it goes positron, what else would it leave behind? Oh, if that's 15, that's 1, it must be 14. Same deal. Oh, if that's 30 and that's 0, that must be 30. So, silicon 30. So one of them, you turn neutrons into protons. The other one, you turn protons into neutrons. And that's the fun thing here with nuclear chemistry, because I told you way back when, like a regular chemistry in the lab, where there's no way for you to change the number of protons. Number of protons is what makes the element the element. Well, nuclear chemistry, all bets are off. Now we're playing God, and we're turning lead into gold, and whatever. We're doing all kinds of crazy crap here, right? So we can do all kinds of things. So now
Can you turn lead into gold?
Yeah, you sure could. In a nuclear reactor, I mean, but yeah, you could theoretically turn it into gold. Yes, okay. Okay, so let's try a couple of these. Positron emission. Let's try carbon 11. Oh, hello, try that again. How many protons does carbon have? Carbon is number 6. So if that undergoes positron emission, it's a little +1 now. What else must it make? Boron, number 5. Boron what? 11 still, right? Because if that's 6, 5 plus 1 is 6. All right. Okay. I think we're getting this. Silicon 26. What's silicon's atomic number?
14.
Okay. So if it undergoes positron emission, what else must it make? Aluminum, which is number 13, yes. Aluminum 26. Good. Okay, try manganese 50. Manganese. Okay, what'd you get? Manganese 50. What else? Chromium 50. So what you got? Everybody get that? Chromium 50? All right, chromium 50. Okay, good. Okay, so there you go. So that's the 4 kinds, the alpha, beta, gamma, and positron. Yes?
In nuclear bombs, what do you use? Do they use gamma? Do they use beta? Or
It's alpha and gamma.
alpha and gamma?
Yep. Yep, we'll discuss all that. So, and they use what's called uranium-235. Okay. So, we just saw that. Okay. Okay. So, now I'm going to present this thing called the activity. So, just because something is an alpha emitter does not mean then that it's as damaging as another alpha emitter, because it has to do with what's called the activity. So let's say then you accidentally ingest an alpha emitter, but it's only spitting out an alpha particle every year. But you also accidentally ingest one spitting one out every second. Obviously, the one doing it every second is going to be doing a lot more damage than one spitting one out every year, right? So that's called the activity. So how active is it? What's the rate then of the disintegration of the nucleus, basically? So how quickly then is the nucleus spitting out particles in a certain period of time? Is it doing, like I said, once a second, once a year, 5 times a year? What's it doing? So we can measure that a few different ways. The most common way, you've probably seen this in movies, is called the Geiger counter. Well, Geiger counter, and they pull it out and it clicks, right? Click, 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 click. We're screwed. Yeah, so that's the Geiger counter. Geiger counter is measuring then the activity. What's it? So what it literally measuring then is the ionizing power. So what it has is it has this big tube like this, and in this tube is some argon gas. So I will draw a little picture here. One of my last crappy pictures for you ever. So here's my tube going over here to my Geiger counter. So I have in here some gas. And on one side I have a positive charge, and on one side I have a negative charge. So normally what happens is these are separated and there's no kind of a current between them because there's no way for the positive then to reach the negative. But imagine that I have some radiation going through the air and it's actually zapping these particles. Well, again, like I said, it's called ionizing radiation. So when it passes through the air, it's going to leave behind a stream of some ions. And if I have some little ions in here now being formed, well, then now the circuit, in a sense, then, it can be completed, and you'll get a little zap of electricity. Zap, zap, and every time it zaps, it clicks. It makes a little clicking sound. Well, the more ions you have, the more ionized radiation around, the more ions you have, so the more zaps you're going to get, the more clicks, in a sense. So yeah, that's basically roughly how it works. So yeah, so it'll click real slow, then it clicks faster than if there's more ions, which means there must be more ionizing radiation being spit out. The other one, which you see a lot like a hospital, is this one. It's called a film badge dosimeter, and you wear that one, you know, in your lab coat or whatever, or your nurse or your scrubs. And then they take it from you every day or every week or whatever, and they develop the film, and they can see, okay, so was there some kind of exposure to radiation? Because any kind of film, you know, where it's like regular film for a camera, back when there was film for cameras, now they're all digital, but regular film for camera, the way regular film works is light comes through, and it strikes the film, reacts with the chemicals, and it makes the film itself change colors, right? Well, radiation is just another kind of light, but it's just not visible. But it is another kind of light. So the radiation then, if it can actually pass through the plastic and smack the film, it'll still make the film change color, just like visible light would. Of course, the visible light though is not passing through the plastic, right? Because it's being sought by the plastic. But the radiation is penetrating. It actually will go through the plastic and still hit the film and make it change colors. And they know, you got too close to that little source of whatever down in the lab or something, and then they kind of know. Okay, well, how do we measure it? How do we quantitatively measure it? A few different ways. One way is called the Curie, which is named for two very famous scientists, Marie and Pierre Curie. Marie Curie, a very famous female scientist, won the Nobel Prize twice. Not bad. Once in chemistry, once in physics. Yeah, named for her, because they discovered. Well, yeah, I mean, under discover, but they definitely studied all kinds of with radiation. So a Curie is 3.7 times 10 to the 10th events per second. So 37 billion a second. So that means, for example, if you have a nucleus or a chunk of something and spitting out 37 billion particles a second, that's one Curie of activity. Spitting out 37 billion a second. That's one Curie. Okay. Events. Another one commonly used, like in medicine, is called the Gray, abbreviated GY. And this one actually measures how much energy, joules, is your body actually feeling or receiving from that radiation. So that's in joules per kilogram of your body tissue. See, that one, like I said, was really trying to measure then the amount of energy and damage your body's receiving. So it's a different scale. And then another one you hear about a lot is called the rad. How many rads? And this is also based off the amount of energy per your body tissue, because a rad is 0.01 grays. Not Gray's Anatomy. Okay. But the one we really mostly use in hospitals and medical settings and such, kind of a combination of these. Are you ready? Drum roll, please. All right. It is called, we're going to call it the REM, the REMs. Now what the REM does is it tries to factor in, okay, so what kind of radiation was it that was hitting you, and things like that. So the REM stands for the Rontgen Equivalent Man, REM. So what it does is it takes the rad, so I just discussed, which is how much radiation then is it per 100th kilogram of body tissue. But now we're going to multiply it by it. Okay, so what kind of radiation was it? If it was an alpha particle, well, alphas we know are really damaging, right? So we're going to count those more. So an alpha particle, you might put in 20 here times the amount of rads you get, because those are really damaging. But betas we know are not as damaging. So maybe for a beta you only put in a 1 times the number of rads. Does that make sense? You just kind of weight it basically in a sense, based on the kind of radiation that was hitting you. We didn't even discuss discuss like a pure high energy proton or a neutron. That might be a 10. So yes, so you take, okay, how much energy was there, joules per mass was there, times, okay, what kind of radiation was it? Was it really damaging? If so, then make the RBE bigger, which gives you more RIMS. If it wasn't as dangerous, if it was beta, make your RBE smaller so you won't get as many RIMS. Okay. So yeah, RIMS is typically the way you'll see it like in medicine. They'll discuss, for example, okay, so how many RIMS is safe? Things like that. Okay. Give a couple more seconds, I'll wrap it up there. Okay, so let's look at some RIMS and see what some values here. Okay. On average, each of us in an entire year, you might get a third of a RIM. A third, 0.33 RIM. So you don't get much radiation just every day. Just like I said, over the course of an entire year, you hardly get any of it. But you notice, though, most of it comes from, surprisingly, not actually the sun. It actually comes from radon. Radon gas is where you get most of your RIM exposure. And then the rest of it does come from the sun and the sky and all the radiation from different nebulas and stuff spitting out stuff on you. And then the next big chunk is medical, right? You use x-rays for your teeth or you break an arm or whatever, you get some radiation for that. And then other little itty-bitty tiny bits here and there. So where does radon come from? Well, radon, like it says, is one of the products in the breakdown of uranium-238. So uranium-238, when it breaks down, it goes through a long 14-step process, which I will not draw for you right now. But uranium-238 goes through all of these steps, step and step and step and step, and at some point it makes radon, which is a radioactive, I think it's an alpha emitter. It's pretty nasty. That's an alpha. Well, radon is a gas, right? It's a gas. So there was all this stuff in the news years ago, and all these people like in the news, they're like freaking out, and everybody was buying these radon detectors for their houses. So basically what happens is, let's say here's the ground, and you find uranium, all over. So like you might have like under your house a big old slab of granite, and in that granite there probably is some uranium just mixed in that granite and things like that. So you have down here, you know, all your bedrock under your house. So you have in here uranium-238, just little tiny bits of it, not much. But then over time, like I said, the uranium breaks down and it eventually makes radon gas. Well, the gas begins to seep up out of the ground. And normally it's no problem because it just seeps up out of the ground, goes off in the air, and it's no big deal. But let's say you come along and you build a house right here. So you build a house right here. Here you are. Here's your house. No big deal because most houses here, at least in California, have a big old concrete slab underneath them, right? So your radon gas comes up, it'll bump, it can't get in the house, and it goes out in the air. Bump, can't get in the house, goes out in the air. But let's say you live in Indiana, where I'm from, back in the Midwest somewhere. Well, now we don't build our houses on these concrete slabs. What do we build our houses on, do you know? Make a big old basement, because we have these things called tornadoes. So we build a big basement down here. We build a big basement down here. And even if there was some gas that gets in your house, well, what happens? What happens? Well, it's no big deal. It's no big deal because the windows open, there's doors open, it all just blows out, clears out of the house. But in the basement, what happens? It goes up here and it just builds up in your basement because it's closed up for days or weeks or months at a time, and then it's like, tornado coming! Everybody runs in the basement. It's just clogged full of radon gas, right? So that is a bad deal. So you get a big giant exposure to radon gas. So now what they normally do with most basements, they'll have some kind of like an exhaust built into the basement, a little vent here to the side, so the radon is being spit out of the basement or whatever, or or like I was saying as well, or then sort of like a radon detector on the wall, so it'll beep and warn them when it's dangerous radon, air out the basement or whatever. Yeah, so anyway, so that's radon, which is where you get that from. So that's just, like I said, just from uranium down to the ground. So now you know. Okay. Like I said, so you might get a third, 0.33 an entire year. You're not getting anything. Well, how much then is actually dangerous? How much do you actually need to get? About 20 is where you begin to see some kind of notable radiation kind of effects and sickness. So you basically need 60 times what you're currently getting, right? So a third times 20, so you need get the third, you get 60 times. So you need a lot more than what you're even getting. So if you happen to go to the doctor a few more times, get a few more x-rays, you're still not going to get anywhere near 20, right? I mean, it's just, like I said, I mean, you 60 times what you normally get in a year, all like, I mean, all very quickly, right? So you need to get 60 times a year worth, boom, right, to really cause some damage. So that's not very likely, unless your job really sucks and you work in a nuclear reactor or something, maybe it's more likely. So what happens at around 20 to 100? Okay, well, that's when you begin to kill off your white blood cells. It makes it harder then for you to fight off infection, things like that, and your cancer risk tends to increase. At around 100 to 400, now you've got full-on radiation sickness, and you're throwing up, and you got diarrhea, you're getting all kinds of lesions and crap on your skin, your skin's peeling off, all that lovely stuff. And then at around 500, you're going to pretty much die. Just a question of how fast. 500 is a couple of months, 1,000 is a couple of weeks, a couple thousand, it's a couple hours. So, yes, like I said, but that's not a concern for most of you at all. So, okay, and that chart, by the way, is in your book, too, if you want to pull that up. That's in your book somewhere. But roughly 20 to 100 is bad, but it's not, horrible at the end of the world. You get some cancer risk and some things like that. But up above 100 is really getting nasty. Yeah. Okay. Well, let's go on here. We still got 15 minutes. Okay, so how do I quantify that? Okay, so like I said, one way is REMS and things like that to actually discuss the amount of dosage you're getting in your body. Well, how about then actually measuring, okay, how many particles are being spit out of that sucker? So that level is called the half-life. So all radiation spits out radiation at a constant rate. So what I mean by that is it's very systematic. So once you know, let's say that how fast uranium-238 is spitting out an alpha particle, it's constant. That's the rate for uranium-238 spitting out an alpha particle. It's not fluctuating. It's not like faster some days or colder some days, or it's not faster when it's hot and slower when it's cold. No, it's constant regardless of the temperature or anything. Has a nice stepwise disintegration. So let's say, for example, you had a sample and you're measuring the disintegrations. How fast is that nucleus thing falling apart and spitting out particles? Well, let's say it's doing it 1,000 times per minute. Okay. Well, at some point, it'll reach, well, now it's turned that uranium into thorium. Turns that uranium into thorium, and there's just less of it left. So at some point, it'll only be spitting out 500 disintegrations per minute, DPM. And at some other point, it'll only be spitting out, half again, 250 disintegrations per minute. So that time that it takes to get to be half as active as it was, that time, that's called the half-life. So how long was it then for it to be half as active? That's the half-life. And once you know that half-life, let's say that half-life is 5 years, or 10 years, or 2 days, or 3 minutes, whatever it is, it's always the same. So if 1,000 to 500 took 5 days, then 500 to 250 will take 5 days. And the next one, at 125, will take 5 days. This again will take 5 days. It's constant. It's steady. Once you know the half-life, again, it's a steady rate of spitting out radioactivity. Okay?
Technically, it won't never stop spitting out because,
until you get down to 0, I guess. Until you get in
oh,
yeah.
True.
Yeah, down to 0. Because you might have, for example, it's 5 million particles now, and there's 2.5 million particles, and then whatever, and then eventually going to have no particles, eventually. But that could be millennia. So call that the half-life, T1/2, the half-life, T 1/2. Okay, well, let me show you a few half-lives here, just to give you an idea, because they really range. I mean, they range literally from seconds to millennia. I mean, it's amazing the range and the activity here. So let me, here it is, right here. Here's my short one. I'll show you right here. So, let's say, for example, a really short one. Technetium-99. That has a half-life of 6 hours. Okay, so 6 hours. Every 6 hours, so every 6 hours, half of it's gone. Half of it's gone. Half of it's gone. So that one's really gone quick. But let's say we have uranium-238. That one takes you 4.5 billion years to get rid of half of it, versus 6 hours, right? So quite a difference there. 4.5 billion years for it to use up half of it versus 6 hours. So this one here obviously is much more active, right? It's really spitting them out fast, right? And it's falling apart and it's cutting it in half. And this one here takes forever to break down. Okay, so let me go back here now. So again, like I said, after every half-life, you have half left, right? So it was 1,000. After a half-life, now it's 500. After another half-life, 250, right? 125. Every half-life, you have half of it left. That's all that means. Okay, now again, like I was saying, that is a steady rate. It does not depend on the environment, on the temperature, on the chemistry of the soil, anything. It's totally independent of all of that, right? It can be hot, cold, whatever you want. Doesn't matter. Okay, so let's just try one. Let's say we have plutonium-239. That comes out of a lovely nuclear reactor, and you got to store it somewhere. Okay, how many years will it take for the activity? So it's currently spitting out 2,000 times a minute. How long will it take us to get down to 625 times a minute? And the half-life for plutonium-239 is 24,000 years. 24,000 years. So we're going to do this the old-fashioned slow way here. Sit down so I can write a little meter. Excuse me. So I start off with 20,000 DPM. So after one half-life, how much will I have left?
10,000.
Half, 10,000. After another half-life, how much will I have left? 5,000. After another half-life, how much will I have left? 2,500. Okay. Keep going over here. Oops.
1250.
After another half-life, I'm going to have 1250. After another half-life, I'm going to have 625. Aha, there we go. So how many half-lives did I have to go through? 1, 2, 3, 4, 5, right? See that? It took me 5 half-lives. Supposed to be a 1.5. 5 half-lives, right? Everybody see that? So how long is one half-life? One half-life is 24,000 years. So it must take 5 times 24,000. 120,000 years. See how that works? So in this class, we'll just always do nice, easy ones like this, whole number ones, no fractions or anything. Come back in 111, we'll do, 2.49 half-lives or whatever. Okay, let's try another one together here. Okay, iodine-131. This is one then that's used in medicine. Let's say you have like a tumor in your thyroid. Typically what they'll give you is iodine-131 because your thyroid loves iodine. So you feed your patient some radioactive iodine-131. The thyroid grabs onto it then. It's very localized now in the thyroid where the tumor is, and just begins to spit out the radiation only into the thyroid instead of spreading all over your body. So, let's say you feed a patient 88 milligrams of iodine 131. How much is going to be left after 24 days if the half-life is 8 days? So, think about this one. 24 days and one half-life is 8 days. So how many half-lives must pass?
3.
Right. So one half-life is 8 days. So yes. So after 3 half-lives, how much would be left? Well, what I'm going to do is I'm going to take that amount and I'm going to cut it in half. What? How many times? 3 times, yeah. Good. Yeah, so I'm going to take 88 milligrams, and I'm going to cut it into half once. And that makes it what? 44. I'm going to cut it in half a second time. I'm going to cut it in half a third time. 11. So there must be 11 milligrams left. Just cut it in half 3 times. Questions? Okay, pull out your handout. You have your hand out there? Let's try. Your turn. Phosphorus 31 is an isotope that's used in the treatment of leukemia. Has a half-life of 14.3 days. If you give us a sample of 8.0 milligrams, how much will be left after 42.9 days? So figure it up. Talk it over. Help each other out. Have one more here. I think I do. Okay, talk it over. Ask your neighbor what they think. What'd you get? Try it out. Okay, how much is going to be left? What do you think? 1 milligram, right? It goes through 3 half-lives. So 42.9 days, real quick here. And 1 half-life is 14.3 days. So yeah, it's 3 half-lives. So now I'm going to take 8 milligrams, 8.0 technically, and cut it in half 3 times. So times a half, times a half, times a half, 3 times, 1.0 milligrams, right? Okay, let's try one more. Iron 59 has a half-life of 44 days. If your lab receives 8.0 micrograms of it, how many micrograms are going to be left after 176 days? Okay, you got an answer? How much is left?
0.5.
0.5. Anybody else? Micrograms, yes. Okay. So 176 days and 1 half-life is 44 days. So we've got to go through 4 half-lives. So I'm going to take 8.0 micrograms. I'm going to multiply it by a half 4 times. Or divide it by 2 4 times. If you want to think of it. So 0.50, I guess. Awesome. Okay. We don't have much left to cover, really, so we'll definitely finish up next week, and then we'll have a little time to discuss the final stuff. So, any questions before we go? So Monday when I see you, we're going to have lecture exam. Then Wednesday we'll have a lab exam. Be glad you're not my other class, which is the Tuesday, Thursday class, because they have their lab and their lecture on Tuesday. They have a lecture exam followed by a lab exam. So at least you have a little break in between. So yeah, we'll see you on Monday.